Welcome to Chapter 4, the chapter this series was built for. Every VQE tutorial you will meet begins with a molecular Hamiltonian that arrived from somewhere else. A library call, a printed table of Pauli coefficients, a file. That is a reasonable way to teach the algorithm and a poor way to understand the calculation, because the interesting engineering is upstream of the qubits. Here we take the hydrogen molecule apart down to the integrals, using NumPy and the math module alone. Every number printed in this chapter comes out of the run, which is exactly what makes the final check meaningful rather than decorative. 5 stages, each producing an artifact the next one consumes. Stage 1 turns basis set parameters and a nuclear geometry into overlap, kinetic, nuclear attraction, and 2 electron integrals. Stage 2 runs a Hartree-Fock self-consistent field loop on those integrals to get molecular orbital coefficients and an energy. Stage 3 transforms the integrals into the molecular orbital basis. Stage 4 applies the Jordan-Wigner mapping and diagonalizes the resulting 16 by 16 matrix exactly. Stage 5 runs VQE against that answer. The geometry is fixed throughout, 2 protons 1.4 Bohr apart. That is a stated choice, not a derived equilibrium bond length. A basis set is a fixed list of functions in which molecular orbitals are expanded. STO3G is the smallest useful one. Each atomic orbital is a contraction of 3 Gaussian primitives, fitted once and published. For hydrogen, there is exactly 1 basis function per atom, and 6 numbers define it, 3 exponents and 3 coefficients. Those 6 are the only quantities in this chapter taken from outside the code. 2 consequences follow. 1 function per atom gives 2 spatial orbitals and 4 spin orbitals, which is why 4 qubits will suffice. And a minimal basis sets the accuracy ceiling here before any algorithm is chosen. Gaussians are used instead of the physically better Slater functions for one reason. Every integral we need has a closed form. The engine is the Gaussian product theorem, which says the product of 2 Gaussians is a single Gaussian centered between them. Only one special function appears anywhere, the Boy's function of order 0, which is what the Coulomb singularity turns into once the integrals are done. It has a removable singularity at 0, so the code switches to a series for small argument. The computed overlap between the 2 hydrogen functions is 0.659, large, because the atoms are close enough to bond. Hartree-Fock replaces electron-electron repulsion by an average field. The orbital equations are nonlinear because the Fock matrix depends on the orbitals it determines, so we iterate. We start from a deliberately lopsided guess, with both electrons parked on 1 atom. 13 iterations later, the energy has stopped changing at machine precision. 2 things to notice. Symmetry is recovered, not imposed. The occupied orbital converges to an equal, symmetric bonding combination that the initial guess had broken. And the total energy is minus 1.116714 Hartree. That is the number the quantum calculation must improve on. The Hamiltonian we want on qubits is written in terms of orbitals, not basis functions, so the integrals must be transformed with the coefficients we just obtained. The 2-electron case is the notorious 4-index transformation. Done naively, it costs order n to the 8th. Done as 4 successive 1-index contractions, it costs order n to the 5th. With 2 orbitals, the distinction is academic, but it is one reason a small molecule is not small. The 1-electron matrix comes out diagonal. Then the cross-check. Rebuild the Hartree-Fock energy from the transformed integrals alone. It agrees to 16 decimal places. That cross-check earns its cost, and here is why. An error in the 4-index transformation is easy to make and completely silent. Transpose 2 index labels and nothing crashes, nothing warns you, and you get a full set of plausible-looking numbers. Downstream, the symptom can be a full configuration interaction energy sitting above Hartree-Fock, which the variational principle forbids and which therefore can only mean a bug. The lesson generalizes far beyond quantum chemistry. Compute a quantity 2 independent ways and compare them. Put assertions where a silent error can enter, not where a crash would already have told you. 4 spin orbitals become 4 qubits. The Jordan-Wigner transformation writes each annihilation operator as a lowering operator times a string of Z operators on the lower index qubits, and that string supplies the fermionic minus sign. Substituting gives an explicit 16 by 16 matrix, and we can do what a real calculation cannot: diagonalize it. The Hartree-Fock determinant sits on the diagonal at exactly the self-consistent field total, validating the whole chain. The lowest eigenvalue is -1.137276 Hartree, giving a correlation energy of -0.02056, exact minus mean field within this basis only. Read the matrix and it tells you how to attack it. The Hamiltonian is block diagonal in particle number and spin, so each sector diagonalizes separately, and the pieces reassemble into the full spectrum exactly. Inside the neutral singlet block, the Hartree-Fock determinant couples to the doubly excited determinant with strength 0.181258, and to the 2 singly excited determinants with matrix elements of order 10 to the -14, numerically 0. That is Brillouin's theorem, printed as a number. Projecting the matrix onto the 256 4-qubit polystrings leaves exactly 15 with a non-zero coefficient. That structure is a gift. Since the ground state has no weight on the singly excited determinants, the whole problem lives in a 2-dimensional subspace, and one parameter is enough: an angle mixing the Hartree-Fock determinant with the doubly excited one. At 0, the state is exactly Hartree-Fock, the standard starting point, and because the ansatz cannot leave the neutral singlet sector, the optimizer cannot wander into another chemical species. About 10 parameter shift steps later, the energy matches the code's own reference value to machine precision, at an optimal angle of -0.225911 radians. Let's recap what changed. The coefficients are no longer invented. Everyone traces back through the 4-index transformation, the self-consistent field loop, and the Gaussian integrals to 6 published parameters and 1 chosen bond length. There is a real approximation hierarchy, minimal basis, then mean field, then exact within basis, and each level has a number attached. Internal cross-checks caught what nothing else would. Symmetry turned 4 qubits into one angle, and the optimized state is still 98.7% Hartree-Fock. This matching proves the implementation, not an advantage. Next, beyond H2, the honest frontier.